she gone?
Listo, Heriberto.
There was a request for live streaming.
Yeah. I see. Yeah, we're about to start. So it's just that so that we can synchronize the YouTube and the Zoom. So I'm going to count 5, 4, 3. Hello, everyone. My name is Heriberto Avelino. On behalf of co-organizers Frida Villavicencio, Rosalía Rodríguez Vázquez, Damián Blasi, and Harald Bayen, I welcome you to the session of the Language, Culture, and Cognition lecture series. Today, we have a very special guest, Dr. Gerhard Jager from Tübingen University. So without further ado, I give the floor to Harald Bayen to introduce our speaker. Harald, you have the floor.
Thank you. So it's a pleasure to introduce Professor Gerhard Jager. He did his PhD at the Humboldt University in Berlin, and then first worked as a postdoc in Berlin and Utrecht University. I think the latter university is a Dutch university, so great choice. He then became assistant professor in Potsdam, where he received a Heisenberg Award. After this, he went to Stanford for some time and then became a full professor of semantics and syntax at Bielefeld. In 2009, he became professor of general linguistics at the University of Tübingen. It seems that Gerhard has truly settled in Tübingen. He has worked for about 14 years in Tübingen, which is more than the 13 years he spent as an itinerant researcher since he obtained his PhD. Gerhard's career started with a deep interest in game theory and Bayesian pragmatics, but his years in Tübingen have seen the flourishing of successful research projects on computational, typological, and historical linguistics. This research has been funded by 2 large grants from the European Research Council, as well as by a grant from the German Science Foundation. It is this line of research that Gerhard will tell us about today. Gerhard, the virtual floor is yours.
Thank you very much. Thank you for the invitation, for the chance of presenting my work. Thanks for the nice, flattering introduction. Harald approached me some time ago and asked me to speak about my work and explain a bit about what the seminar is. And I decided to pull out a piece of work which I actually performed a few years back. And it's fresh on my mind because I started redoing this in the light of newer methods in statistics and machine learning. But today I'm going to present you a ready and dried version of it. So the world tree of languages, so this is something people have dreamed about since quite some time. Of course, you could argue that such a thing doesn't even exist, because if you believe in polygenesis, then there is not a single tree. But if one believes that human language evolved once and that all existing languages kind of derive from this original language, then it should be possible to arrange them in a family tree. What I'm going to present is not this family tree. And actually, the more I worked on this, the more skeptical I became about whether this is possible. But it's the best I could do given the data and methods available, and it's still a very useful tool, both for studying the relationships, historical relationships between languages, and as a stepping stone for all sorts of statistical investigations about language diversity and also population diversity. I'm happy to answer questions, but I guess this is technically difficult. So first, a few words about how evolution and language belong together. I guess I'm talking to the choir here. So it's known since the 19th century that there is an interesting parallel between the diversification of species in biology via the separation of subpopulations and then their subsequent diversification via a process of mutation. And a similar process regarding languages. Of course, we're talking about very different timescales here. but the process as such, or the resulting structure, looks remarkably similar. So the founders of the respective fields, Darwin in biology and people like Schleicher in linguistics, were well aware of this. So there's this famous Darwin quote, which I won't bore you with reading loud, but Darwin in The Descent of Man, he specifically referred to this parallel, and he also assumed that there is a parallel regarding the process and not just the resulting structure. Some very superficial indications about the similarities. So if we look synchronously at different languages, so here I have from 4 languages, all Germanic languages, the first line of the Paternoster. And you clearly recognize, okay, these languages, they are pretty similar, but they are not identical. And if you know a few more languages, so it's enough to know something about Latin, not talking about Nahuatl or something, then it's pretty clear that this is there must be a historical explanation for the similarity. And this kind of variation among similar species is also something which kicked off Darwin's thought process. So the beaks of the finches, for instance, so they are clearly similar, but they are not identical, and they differ in an interesting way. Good explanation for this diversity and similarity is to assume that different varieties, both in biology and in linguistics, they evolve from a common ancestor, and then different lines split, so population split. We are always talking about populations here. They split and they replicate with variation, and then in different lines of subpopulations, this variation goes into different directions, and then we end up with a tree-like structure, and we observe the leaves of the tree. So here, for Germanic languages, this might be something like this, and for finches, it might look like this. Sometimes, when we are lucky, then we even have a longitudinal attested data. So for too few languages, but for a couple in Europe and East Asia and West Asia, so we have, and then South Asia, we have historical records, and then you can actually observe diachronically how this change took place. So this would be going from High German, this was the first example here, to Middle High German, which was spoken something like 800 years ago, to Old High German, which was spoken like 1200 years ago. And then we don't really have attestations for earlier distant ancestors, but Gothic is close to an ancestor which goes another 500 years back. And we find something like this also in biology occasionally if we have fossils. So you can we have fossils from different stages of the evolution of the horse, for instance. But yeah, this is rare, as I said, especially in linguistics. This is rare because writing is very unevenly distributed across the world and across language families, and it started fairly recently, looking at the history of humanity. So mostly we would just have to work with extant data. I could follow on and on about these similarities between language change and biological evolution, but this is not my main topic. So just one more example here. We also find something like convergent evolution. So for instance, wings have been invented by evolution at least 3 times in biology. And you find something like this also in language. So this is perhaps not a very good example because it's a poor chance similarity. So the English word dog, so the translation of this word into the Australian language, babaram, is also dog. And you can actually, via reconstruction, you can actually see that here we have convergent evolution. This is a poor accident, but there are more substantial functionally motivated processes of convergent evolution, so that we, for instance, find ergative case marking systems in Australia and in the Caucasus and in the Americas, because this is just a good solution, perhaps not the best, but a good solution to the problems we can encounter when coding the messages. And also, when we want to reconstruct how the observed diversity evolved, the processes in biology and in linguistics are similar. So in linguistics, I suppose that most of the listeners are aware of this. There is a tried and tested method called the comparative method, which traces back to the 19th century. It's an iterative process, but it involves at least the 3 steps, namely, if you suspect that a group of languages are related, have a common origin, then you have to identify homologs or cognates, so words or grammatical morphemes, sorry, Harald, so morphological features, however you call it. So features in the putatively related languages which are similar, which are good candidates of having been derived from the same ancestor, like English New and Slavic Novi, or tu and dva, or water and water would be examples for cognates. And here you can see it with the bare eye, that these are good candidates for being related. Once you've done that, then you can try to construct a common ancestor. So you have to make decisions like whether the T here or the D represents the ancestral state, and then there are good heuristics. And if you compare many such cognate words, certain patterns emerge, so you can form a plausible hypothesis about what the common ancestor looked like for these cognate words and what processes led to the observed variation. To carry this out, you have to stipulate a tree, a family tree. And once you have a family tree, you might have to revise your assumptions about cognacy, etc., etc. So these steps are repeated until you get a coherent picture. And of course, people keep arguing. So Indo-European is the language family, which was the first one which was studied by this method, and which has been investigated most intensely, and people still argue about certain aspects. And the further you go back in time, of course, the more difficult it gets to get a coherent picture based on tested and agreed upon heuristics and principles of language change. So in this process, as a side product, the scholars reconstruct the vocabulary and partially the grammar of ancestral languages of nodes in the tree. But of course, the vocabulary of languages changes. We borrow words from other languages. Certain words just get old-fashioned and drop out of usage. So the vocabulary is a live thing. It's not just that sounds change, but also words are being replaced. So the further you go back in time, the smaller the size of the vocabulary is that you can reconstruct. And there is a consensus that there is a time limit of between 6,000 and 10,000 years. So people disagree a bit about what level of uncertainty they are willing to accept, but it's certainly post last ice age time depth that we can reconstruct this way. There has been some debate that words and cognates between words are perhaps not the best indicators of relationships between languages, and that grammatical features, aspects of language are more stable. But the more this is being tested, the less clear the picture is. So it seems like that a lot of syntactic features are actually also very frequently borrowed between languages, so they are not necessarily indicative of common descent. Morphemes are actually more reliable, but the difficult thing about morphemes is that they are very specific for different branches of a language family, so it's hard to make a large-scale comparison. But yeah, there's still ongoing research and disputes about what kind of features we can use to apply this kind of method. And then it has been argued, this is also controversial, that this method, which was developed with Indo-European in mind and then was applied to other language families, that perhaps it's not even appropriate. So Robert Dixon made this case in a book from the 1980s, The Rise and Fall of Languages, where he said that in Australia, where we had kind of an equilibrium for tens of thousands of years, and not this rapid spread of a single technology and the language together with the technology as we had in Europe perhaps, or in North Africa, then this tree model is actually inappropriate. But this has been disputed as well. So it seems like the comparative method in principle is applicable for all language areas and all continents. Now, a lot of this involves repeated comparison of strings, right? And this is something the computer should be good with. So since the 1980s, so since people had access to cheap PCs, linguists have tried to automatize this process to a certain degree. And biologists did the same with more success, arguably. So this computational phylogenetics. So this is the statistical and computational implementation of something very similar in biology. And biologists are in the lucky position that they have DNA sequences and protein sequences. And here the transmission is well understood. You have discrete, so strings of discrete symbols, not very many of them, 4 for DNA and 20 for amino acid sequences. And these sequences are very long with thousands or tens of thousands of letters. So they have a lot of data and they have a fairly simple process which can fairly easily be modeled in a statistical model, and these things taken together led to an explosion in computational methods in bioinformatics, which do this reconstruction of the tree and of the ancestor states automatically. And starting in the late 1990s, I think, several adventurous computational biologists figured out that, well, actually, this is something which should be applicable to language history also. So unfortunately, I have to admit as a linguist that it wasn't actually us who picked up these new ideas from biology, but the biologists or bioinformaticians brought it to us. But many linguists, including myself, were very excited by this. So Russell Gray was one of the early pioneers, and Mark Pagel from Reading, and several others, but these are the most visible ones, I believe. I'll talk a bit more about the technical details, how we can adapt the models from biology, from molecular evolution to language change. So in general, so both aspects of this comparative method, namely discovering cognate words and constructing trees automatically, are things which in principle computers can do. We have algorithms for this, and this has a lot of advantages, of course. So it's easy to scale this up to hundreds or thousands of languages. You have all the advantages which come with the natural science method. So it's transparent. In principle, if people do it properly, then all the data and the code for the computer programs and all the statistical assumptions are visible for somebody who wants to replicate it. So it's replicable. You can modify transparently your underlying assumptions about what kind of statistical process you use, and something like this. So this is, of course, an advantage as compared to the traditional humanities method, where every scholar basically has his or her implicit assumptions, which are not always entirely transparent. But of course, there are disadvantages. So far, humans are still better than machines. So the first step, doing cognitive judgments. So this is not as simple as the few examples I showed you seem to indicate. So one of my favorite example is the Latin and the German words for head. So in Latin, it's caput. In German, it's Kopf. And if you look at these two words, you would say, okay, these are great candidates for being cognates. You have a K at the beginning, and then you have a P, so very stable sounds. So, okay, and they mean the same, so they're probably cognates. But if you study a little bit about Indo-European, especially about the Germanic branch, then you know there was Grimm's law, and a K in Latin actually must correspond to an H in the Germanic branch, and the cognate of caput is actually English head, and in German Haupt, which also means head, but it's a bit outdated. It's on its way out, at least in the meaning head. And the word Kopf, this is actually the result of a semantic change. So it used to mean cup, and it's cognate to the English cup, and both words are borrowed from Latin, cuppa. So there is a relationship to Latin, but not what you would think. So it's very easy to have false positives because of this chance similarities. They are pretty frequent because there are only so many sounds in human languages and words are short. So we find chance similarities, and also after thousands of years, words change their shape so much that it's often not possible to recognize cognates without really knowing the sound laws. So for instance, Russian stoch and English 100 are partially cognate, and nobody would guess this. And there a lot of work has been done into automatizing cognate categorization, but so far the results get the low-hanging fruits, but not the higher up fruits. And also with 3D construction, so the picture is a bit better, but when linguists, classical historical linguists construct their trees, then they also have their ideas about prehistory in mind. And well, in the computational branch, people have started doing this as well, but you can't have these information, or you can't inform your model by plausibility considerations, which is a good and a bad thing at the same time, I suppose. Okay, is that much about the broad research landscape, and now I'm going to talk about my own approach in my that I pursued in my project for carrying out a real pipeline from primary data to a tree. So from words to trees. So I start with a mini vocabulary list, then using statistical and machine learning techniques. First, I train a model which recognizes sound similarities, so which sound pairs are good candidates for being related historically. Then this enables a systematic comparison of words which are candidates for being cognacy, and then using clustering to approximate the classification of words into cognate classes. These cognate classes can be used as features, and they can be fed into the algorithms which the biologists or computational biologists kindly developed and programmed for us. So the last part, the actual tree inference, is something which has been studied intensely and to a large degree solved in computational biology. So I can feed the result of these computational linguistics pipeline into phylogenetic inference, so into a tree inference pipeline, and then at the end I have a tree. So a hypothesis about the history of languages, the diversification history, and yeah, this is an interesting object in its own right, and also it's a helpful stepping stone for further studies. Okay, so I forgot to show you the illustrations, but I go over each step in more detail anyway. So first step, from word lists to distances. So most people working in the field actually start a bit later. They start actually here and they do the first step manually. So there are a lot of databases around, and this collection is growing almost by the day and certainly by the month of data sets with manual cognate classification. And so a lot of information from classical historical linguistics goes into this, and then a lot of the uncertainty which is involved in the first steps is taken over by humans, which have some domain knowledge. But these databases, they are always confined basically by definition to individual language families. And there is a certain circularity, or in any event, this is then not independent of the traditional method, because the decision what is a language family, well, the definition of a language family is a maximal group of languages of which it can be demonstrated by the comparative method that they are related. Well, it's not really a definition because the meaning of the word demonstrated is very vague. But cognates can only occur inside language families, right? So you have to restrict the scope of your study before you even start doing the study when you rely on manual cognate classifications. There's a great database which covers in the meantime 7,000 languages and dialects. So the version I used to conduct the study was at 6,000 languages and dialects. It's called the Automated Similarity Judgment Program. It started, I think, in 2008. Sören Wichmann, back then at Leipzig, now at Kiel University, kicked this off. So he and his co-workers, Eric Holman and some others, figured out that using some pilot study that actually if you only have just a translation of 40 core concepts, namely these 40 concepts in a set of languages, then you can already make pretty informed automatic decisions about their degree of relatedness. The standard opinion is, or the tradition, let's say, is that you need 100 or 200 concepts. So there's this famous Swadesh list or Swadesh lists, which was actually, Modest Swadesh, who pursued the project, which is kind of an early forerunner without computers in the 1950s, came up with sets of concepts of which he thought that they are fairly stable diachronically and resistant to borrowing, and that they might be good indicators of relatedness. And Wichmann et al. Found in their pilot study that we can actually get by with just 40 concepts. And you see what kind of concepts these are. So IU, we, 1, 2, person, fish, dog, louse. So yeah, very basic vocabulary, which is not culture dependent, except perhaps dogs. So not every population might have a dog, and not every language might have a word for dog, but otherwise this is pretty universally applicable. And then Wichmann and co-workers started to simply contact people who know languages and ask them to translate these words into the language the informant knows. So it's breadth over depth. It's not necessarily native speakers which supply these word lists, these translations. Partially they come from dictionaries, partially they come from just the knowledge of field researchers or otherwise experts. Also the transcription, this was designed to use only ASCII characters. So there are only 41 different symbols, so it's very coarse-grained. If you compare this to IPA, which is actually the standard for this kind of data collection. And here I show you the example list for Latin and for English, just to give you an idea what these transcriptions look like. So you can more or less guess, I suppose, what the meaning of the different symbols is. Then there are some diacritics, so for indicating nasalization and things like this. Or this means if you have this tilde, this means that the preceding two segments are actually one segment, and the second one is only an articulation diacritic. But for my study, I threw out all these diacritics and just wrote with the strings of ASCII symbols. The next step is to identify candidates for cognacy, and string comparison. This is something computational linguists do a lot, and the standard first step is to try an alignment or to compute the edit distance between trees. So this is actually, these are different perspectives on the same thing. So an alignment of two strings means, so here I picked the German word for hand, which is Hand, and the English word, which is transcribed like this, hand. Alignment means you look for the pairing between between symbols in one string and the other string in such a way that no lines cross, but you can insert gaps on the one side or the other side. And then you check how many of these pairing, and you maximize the number of matching connections, right? So here we have a match, here we have a mismatch. So here we would have a 50% match. But this, so from with the eyes of a linguist, sorry, this is very coarse grained. So here just another example. So also the German word for hand, comparing it to the Spanish word for hand, which is transcribed like this, mano. You also get a 50% hit rate or match rate, and this is poor chance. And the fact that, well, here the mismatch between a T and a D is much less severe than a mismatch between an H and an M, for instance. This kind of information, this is clear for a linguist, but not for the machine at this stage. So perhaps you want something more fine-grained, so which distinguishes sounds according to their properties. So I'm skipping over some of the details here. So here are more examples of where this approach screws up. So for instance, the German word for two is zwei, transcribed like this. So we have this affricate sound at the beginning, which is clearly cognate to the English T in two. But these are different symbols for the alignment algorithm. And here a voiced Z and a voiceless S in Nase versus nose would not be recognized as being related, etc. So this doesn't work very well, but there is a well-established method to improve this, and this has been reinvented several times. I actually got it from a bioinformatics textbook, and then I was informed by John Narbonne that he and the people in his lab have invented exactly the same thing for in the context of comparing dialects. And there might be more people who have invented this. Now the next step, improved version of this alignment approach, is to have weights for pairings and not just compare matches and mismatches, but to have something like a penalty or a reward. So pairing an H with itself brings a reward. Pairing a T with a D might still bring a reward, while pairing an H with an M brings a penalty. So that's the idea, but we need these rewards or penalties, and there's a systematic way of doing this, which is given by this formula. So this is sometimes called the log odds or the pointwise mutual information. This is the name I adopted. So if you want to know whether, let's say, a T and a D, what is their degree of similarity, then we need to know the probability that these two sounds participate in a sound correspondence. So this is here the numerator. In the denominator, we have the probability of these two sounds being paired by chance. And this is just the product of their individual probabilities. And if two sounds have a propensity of participating in a sound correspondence like D and T, then this will be larger than this. So the entire fraction will be positive. The logarithm will be larger than 1, and the logarithm will be positive. And otherwise, if two sounds kind of repel each other, like a vowel and a consonant, the whole thing will become negative. But to estimate this, well, we need to know these probabilities. The probability of individual sounds, that's easy. I just counted how often the individual, so the 41 sound classes occurred in this entire collection of data from the world. That's statistically not perfect, but there are so many data that this is good enough. This is harder. So the probability of a pair of sounds to participate in a sound correspondence. And here I used heuristic approach. So first I used a very coarse-grained heuristics to identify pairs of languages which are similar. And this was estimated on the basis of really just the simple-minded algorithm, alignment algorithm. And so here are just a few examples. So my personal notation is that the first 2 letters or 3 letters indicate the language family, then the subfamily, and then the actual names. And you see that this heuristics basically always gives me pairs of languages which are from the same subfamily, same genus. Then in a second step, I pick such a pair of languages, let's say 2 Penutian languages, both from the Maiduan subfamily. These are actually 2 dialects of Maidu, it seems. Then I pick a concept, let's say 1, and then I pick the translations for this concept in these 2 languages. So I have Nizam and Nishem here. Then I align them according to identity. And because 3 of the 5 sounds are identical, these non-identities, so they are kind of squeezed into the right pairing. I do this thousands of times. And then I count the pairings. And this is a rough estimate for this probability here. And then I repeat the process. But then I do the alignment based on the weights I got in the previous step. I'll show you in a minute how you align 2 strings with weights. I repeated this 10 times, and then the weights were relatively stable. So how do you align 2 strings with these pairwise weights for sound pairs? So here is an example. So this is the German word for person, Mensch, and this is the Cimbrian cognate thereof. So Cimbrian is a German dialect spoken in northern Italy, and here the word is Mennes, sorry. And how do we compute the optimal alignment between the 2? And now the optimal alignment between 2 strings is the pairing between the individual symbols in such a way that the sum of the weights for all the connections is maximized, or the sum of the rewards, so the sum of these PMI scores. There are astronomically many different possible alignments, but fortunately you can reduce the problem to a smaller problem. So if you know the optimal alignment between, let's say, Männer and men, and between Männer and Mensch, and between men and Menes, then you can easily compute the optimal alignment for the entire string. So you reduce the problem to aligning of shorter strings. So technically the algorithm looks like this. So we have to decide on a penalty for introducing a gap, and these were also I used the heuristics to get these penalties. And then if you want to fill a cell, so this basically tells us the optimal score of aligning M with M. You have 3 choices. You could align M or match M and M, or you could introduce introduce a gap on the one in one string or a gap in the other string. So these are the three arrows. So and you only have to look at three values which you computed previously, and you take the maximum one. And then you have to fill this array. The number down here gives us the aggregate score of the best alignment, and we can actually figure out the best alignment by backtracking how we got this this optimal value here. And oops, I should have shown you the optimal alignment. Can I write this here? So, and it's of course what you would expect. So these two S's are aligned, of course. And in general, so this approach gives you alignments which are not perfect, but which look much more reasonable than the ones I showed you previously. And also all the similarity scores between sounds. So this actually gives us an interesting classification of the sounds. So basically sounds are classified according to the place of articulation. So vowels form a class of itself, and then we have labial sounds having a strong similarity to each other, which indicates that a labial sound often changes to another labial sound, and a dental sound often changes to another dental sound. So a sound change most of the time keeps the place of articulation intact. So this is basically the message which comes out of this statistics. And well, we do have expert cognitive judgments, so we can actually check how well can we predict those with these word similarities. And here, these are the similarity scores based on edit distance. So on just identical or not identical sound, the red ones, so this means these are the distances between non-cognate words, and the greenish bluish ones are for cognate words. And here's the same for this pointwise mutual information similarities. So we still find a lot of overlap. So there are a lot of chance similarities between non-related words, and a lot of cognate pairs which are not very similar to each other, but the separation certainly became better by using this more sophisticated method. And so this gives us a method to compare words. I think I have to speed up a bit. Next step is to determine the distance between languages. And then here the example is, can I get rid of this annotation somehow? Yeah. So suppose I compare English and Swedish, then I have 40 words for English, 40 words for Swedish. And then I compare the word similarities between synonymous words to the word similarities to non-synonymous words. And I find for, so this is for English versus Swedish. So here in the blue graph, you see the distribution of word similarities between pairs of words which have a different meaning, so which are most of the time not cognate. And the red one here, the distribution is the pair of words which are translations of each other. And you see this nice bimodal distribution up here. We have the cognate pairs, down here we have the non-cognate pairs. And then by just quantifying how the discrepancy between the two distributions gives us a good measure of the degree of relatedness between two languages. Then in the next step, we can use these measures to classify cognates. And here I used the supervised learning approach. So I took data from the before mentioned databases where people manually annotated cognate classes. And I used two measures to predict cognacy from ASJP, namely the similarity of the words. So if I compare two words and I want to decide are they cognate or not, so I compute their similarity and I compute the distance between the languages they come from. And the red dots represent cognate pairs. And you see we find cognates usually between languages which have a low distance and the words are similar, right? And while random pairings are distributed like this, but again, we have a large overlap of words between highly divergent languages with a lot of sound change intervening. So it's not possible to separate the two classes perfectly, but I did my best to approximate this. I used the so-called support vector machine, which for each data point gives a probability of this representing a pair of cognates. And then for each, so all translations for person, for instance, among these 6,000 languages, I compute these two measures. So I get 18 million word pairs. And then I can extrapolate from these hand-annotated words to non-annotated words, and I get a probability that two words are cognate for each pair in this database. And then the next step is clustering. So suppose here, for illustration, I just have a few Romance words for person. So we have different versions of Latin persona, and then we have different derivations of Christianus from late Latin, which adopted or assumed the meaning human being. Here the numbers on the edges on this graph are these probabilities. And then I use the clustering algorithm called label propagation. So first, each node in this graph is a separate class. And then you pick out one node and you find the neighbor which is closest and assign it the same cognate class, the same cluster. Yeah, actually, I made a mistake. But sorry, I explained this the wrong way. So for each node, you look at the classes in its neighborhood, colors in its neighborhood, and then if two neighboring nodes have the same color, then you just sum the probability, and then the color which get largest joint probability wins out. So here one is larger than the other two numbers, so this gets the same color than this. Then here we have actually free choice, and then we randomize, and then you loop through this network until nothing changes anymore. And in this case, we get a nice partitioning into cognates of persona on the one hand and cognates of Christianus on the other hand. And here, just for illustration, so this is what the clustering looks like on a larger collection of Romance languages and dialects. And also I threw in Albanian here for comparison. So you see that, for instance, Ombra and Omo are put into different clusters because this B, the algorithm considers this B as an indicator of dissimilarity, even though we know these are cognates, and then all the versions of persona go into one cluster, but then different versions of Homo go in various clusters. So we have here, we have Oma, we have Omini. So we have a lot of false negatives, and also somewhere here we have somewhere there was a no, here there are no false positives, but you see that, well, the classification we get, it makes sense even where it's not in agreement with how a linguist would classify cognates, because the subpartition of this class of Homo, well, they are partitioned according to characteristic sound changes, and this is also something which tells us something about the history. Yeah, I think I jump over this for reasons of time. So now we have cognate or approximation of cognate classification. In any event, we have a partitioning of the words for the different concepts for each concept in this database. And now the statistical model, which is just adopted from biology. The idea is if you have a feature in a language which can take different discrete values. So it could be SVO, SOV, or at preposition versus postposition, could be typological features, or the language has a cognate of Christianus as the word for person. This would also be a feature, and then we have 1 or 0. 1 if such a cognate exists, and 0 otherwise. And then the model, so the stochastic process modeling language change simply assumes, well, the language jumps between different states. So by totally non-deterministic random process. So at some point, a language decides I throw out one cognate class and assume another one. And so how probable such mutations are depends on the parameters of the model. And then we have to assume a tree or a phylogeny, so a tree with branch lengths. And then if a language splits, then the state of the language is copied onto the 2 branches, but then the same process happens independently on the subbranches. And then this leads to a distribution of states at the leaves. And statistical inference goes this process backward. So this is how we pretend that God generated the data, or nature generated the data we observe, and statistical inference means we do reverse engineering. So we make observations and then we compute the probability of different histories for producing the data we observe. So we can infer a tree or a probability distribution over trees, and also actually the history. Of course, we cannot certainly infer the truth, but we get a lot of uncertainty. And depending on what kind of statistical inference you use, either you have a point estimate with a lot of uncertainty, or you have an entire probability distribution for this. Again, I'm jumping over a few details. Oh, that's perhaps interesting. So I also look at other ways of assigning features to languages. And then I infer the tree and compare the tree to an expert tree. And there's a distance measure called the generalized quartet distance, which compares the similarity of 2 trees. And 0 means the two trees are perfectly compatible. They need not be identical if we have multiple branching trees, but they are perfectly compatible. And if I combine these automatically inferred cognate classes and then some very surfacey, shallow features about the occurrence of sound classes in the words for certain concepts, then I get the value of something like 7%, which is comparatively good. So you can say that using these features and then phylogenetic inference, we can infer trees which are pretty close to the expert classifications for the time depths and for the families where we have reliable expert classifications. But I'm not confined with this data set to one language family, but I can infer a tree for the entire collection of languages. So this is the world tree I promised you in the title of the talk. So this is a nice colorful rendering of the world tree. Of course, it's not possible to show you any kind of detail because there are 6,000 leaves here on the tree. So I try to illustrate a bit what's going on by having here color coding for the for the continents or the macro areas, and you see that we have a strong geographic signal. So it's not perfect, but you see that we have a huge African cluster, and then the colors of the branches represent language families according to the Claude classification. And you see that Atlantic Congo, a large part of which is Bantu, form one large group. And then here we have, I think, these are the Mande languages here, the brown ones. And then here we have Afro-Asiatic languages. So they are next to the Niger Congo, but they actually belong to a different branch. And here we have something which looks intriguingly like Nostratic, you know, this putative macro family, which comprises a lot of Western Asia and Europe. So Indo-European is somewhere here. I think this is in the European, and then we have Guralic and the Turkic languages, and here this is Afro-Asiatic. Also, we have all this is Australian. No, wait. No, I'm confused myself. No, these are the Austronesian languages, so another big language family which is perfectly recognized. So I didn't help the tree inference finding language families. And the Papua, and then we have a lot of Eastern Asian languages. And what is nice is that, you know, in Papua, we have extremely high diversity of languages, but the Papuan languages actually end up in two clusters, and one of these two clusters also clustered together with Australia. So we get a very strong geographic signal on the higher levels. On the lower levels, this approach more or less reproduces the traditional classification. And it is tempting to say, okay, I proved that there is Nostratic and I proved that there is some Sahul cluster, but actually I'm not sure anymore how to interpret this, because using tree inference means every variation between languages is interpreted as the result of vertical transmission. So this algorithm knows nothing about language contact, and everything which is transmitted horizontally is reinterpreted as common ancestry. So my suspicion is that these nice geographical clusters are, or could as well be the result of diffusion. So in the Americas, for instance, so where do we have North America here? So no expert except Joseph Greenberg and Marit Ruhlen would cluster these languages together into one macro family. And also it's not consistent with Greenberg's classification either. So it might very well be that within the last 12 to 15,000 years, there was so much diffusion going on in North America that there's just enough similarity for the tree inference to believe there must be a common ancestor. Okay, so there's a nice result. The interpretation is somewhat open. But even if we can't be sure that this really reflects human history, it's only an approximation, it's still useful for downstream applications. So for instance, one study I did was about the typology of case marking. So, you know, we have accusative, nominative, accusative languages and ergative, absolutive languages and mixed systems and languages without case marking. And there's a lot of debate about possible functional justifications for this. And also people observed early on, so Elena Maslova, I think, was the first to make this point that actually it's not very helpful to just count how many ergative languages we have, and how many accusative languages. Because many accusative languages, for instance, come from Indo-European and Austronesian and Bantu, the big language families, and it might be that they are just overrepresented because these families are so big. So we cannot treat individual languages as individual samples and then do statistics with this, but rather we should try to estimate the transition rates between different states. And then if the transition from ergative to accusative system is more probable than the reverse transition, then we have something which might be linguistically interesting. And this is a first step of doing exactly this. So these two red clusters here, so this represents a poor accusative system, and this represents a differential object marking system like most European languages. And then the ergative languages are up here in different versions, so in greenish. So and then the size of these arcs here represent the equilibrium probability. So the probability, the estimated probability, if you follow a language over hundreds of thousands of years, how much time will it spend in the different states? And at least this study seems to indicate that there is in fact a very strong preference for accusative languages over ergative languages. And within ergative languages, yeah, that's perhaps linguistically relevant. And if we have a partial accusative system with differential object marking, then using one where, as in Latin and English and Hebrew and Turkic, etc., a system, or Spanish, a system where prominent objects have a special accusative marking and non-prominent objects look like the nominative. Such a system is much more likely and much more stable than a system where it's the other way around. So this would be, so excuse my idiosyncratic notation here. So this would be a system where, for instance, inanimate objects would have an accusative marker, but animate objects would be identical to the nominative marking. So this is extremely unlikely. So this is something observed first by Silverstein, I believe, that we have this asymmetry. And figuring out the diachronic speed of the diachronic processes and then comparing those kind of justifies this finding, which typologists mostly agree on based on the synchronous distribution. But based on the synchronic distribution, this has been disputed, and going via diachrony might be a cleaner way to identify such symmetries. Okay, so my time is up, I believe. So thanks for listening, and I'm looking forward to questions.
This is great. Thank you very much. Harald, do you want to start with some questions now that you have the floor?
Well, I have, Fabrizio has a question. I saw a hand.
Yeah.
So maybe he should go first.
I actually no. I just it was like those clapping hands.
Oh, clapping hand. Then I will. I would like to go back to your colorful world tree, because I would like to understand the graph a bit better. So it seems to me that some colors are distributed in various. So the orange, which
this is Papuasia, so this is Oceania and Papua, so island Southeast Asia and Papua.
Yeah, but so the orange on the left, and then you have orange in the lower right. Yeah. That's the same language family?
No, not at all. So this is Austronesian, and we know from linguistics, from genetics, from it's totally settled that they came from Southeast Asia, from Taiwan actually, and from Chinese mainland. And this happened like 5,000 years ago. It's a very recent, in the great scheme of the grand scheme of things, a very recent process. And these are the Papua languages here. Which so for all we know, these are the languages of people whose ancestors got there 60,000 years ago.
Yeah,
they are totally unrelated. There's a lot of borrowing going on in both directions, but genetically they are totally unrelated.
Yeah. Okay. And then the Eurasia, there are a couple of groups.
Yeah. So we have. So yeah, there seems to be a clear north-south divide actually in Eurasia. So you have Europe plus Turkic languages, so basically the steppe and Siberia. So this is this cluster, so which one might dub Nostratic, if you like, but without Dravidian. So it's really the Turkic, Mongolic, Tungusic, Uralic, Indo-European, Kartvelian, I think. And then we have the Southeast Asian language families. So I'm not 100% sure, but I guess this is Sino-Tibetan here, and this is Austroasiatic, and this is Tai-Kadai or something like this. So these are these Asian language families.
Okay. Yeah.
Yeah, and then this is interspliced with American languages, so the geographic signal is not everywhere reliable. Also, Japanese stubbornly insists on being an American language. This is here.
And where's Korean?
I don't know, but I didn't find any signal at all that Korean is somehow related to anything else.
Yeah, because it's you know, I've been doing a little bit of work on Korean morphology, but it seems to be a real isolate, and that's you can confirm that.
At least based on these 40-item word lists. I just read a paper the other day where somebody claimed on the basis of morphological data that there's a signal for grouping Japanese and Korean, but there's no signal to connect them to the rest of Altaic, as has been claimed.
So what do you make, you know, if you look at aspects of the language at a very different level, like, you know, how you deal with honorifics, with politeness, then there are some striking similarities between Japanese and Korean. But they're probably not lexical. But I'm just curious, do you know of any work where people are looking at these politeness systems of, you know, different kinds of pronouns depending on the status, the relative social status, the respect you pay to other people? Because it seems a bit of a kind of, I'm very limited in my knowledge about these things, but although Korean and Japanese do not appear to be, say, related in this phylogenetic sense, they have a lot of cultural similarities in what they do with their language at this kind of how they manage politeness.
I'm not aware that anybody looked at honorifics specifically for you know, this classification task. People look at other aspects of grammar, of course, as I mentioned, but to do this, you know, in this kind of framework, in this Procrustes beds, you need features which can be applied to each and every language. So this limits morphological comparison to a certain degree, because often the categories simply don't carry over. And I could imagine, I never looked at this in detail, but I could imagine that this is also something which changes quickly. So if you look at how quickly in Western Europe, you know, the second person plural for you know, for as an honorific
politeness
is disappearing, or in English it was the other way around, but the, you know, the to distinction is just disappearing quickly, and it's clearly a result of social change. So I could imagine that something like this also applies to these more elaborate honorific systems. So it's interesting for studying language contact and co-evolution with culture, but probably not for finding deep relationships.
I have a somewhat unrelated question that is still related to the general topic, and that question has to do with the spoken language. So it's amazing what you can do with 40 words and a kind of high level description, but a lot of words, especially in context, can be reduced tremendously. Words like eigenlijk or eigentlich in German, eigenlijk in Dutch, reducing to ak, and you would not recognize the word in isolation, and you put it in context and everybody is saying it all the time. So this is a kind of lead in to a more general question that I read about. This was something that Greg Corbett, the British morphologist, brought to my attention. But there is I think a statistician in Oxford or Cambridge, and they were talking about trying to reconstruct the sound systems of how Proto-European would have been spoken and so on from the extant audio signals of the languages we have.
Cool.
And I am just wondering, is this at all possible? It would be very nice to have a kind of audio to listen to Proto-Indo-European or whatever.
I had this idea together with two colleagues from Switzerland, so Chandra Cathcart and can't remember the name from Neuchâtel right now. So we just looked at Germanic dialect. There's this nice database of Swadesh lists with sound recordings, and we tried to use deep learning systems or speech to text. So sending it through a deep network so that we have a vector, and then using the vector for ancestor state reconstruction, and then sending the vector back into a speech synthesizer, and it didn't work at all. But we didn't spend a lot of time on this. So in principle, I don't see why not. But that's, I mean, this is the direction research should go, definitely, because I spent a lot of time earlier to explain why using manual cognate judgments is kind of a bit dangerous, but using manual transcriptions of words is actually the same thing. So it goes through the head and the reflection of whoever writes the dictionary, right? So in the end, working with audio recordings is the proper thing to do. So the way like biologists do it, basically.
I think it could be interesting, but it is fiendishly difficult, and you almost have to give up on. So, and then it again depends, if you use a kind of high level, high register standard dictionary pronunciation, you get something completely different from if you have the vernacular. Even vernaculars are spoken by highly educated speakers. I can play you some differences between, say, standard Mandarin pronunciation and colloquial Taiwan Mandarin. Educated university people. That this work by Keith Johnson on English, that 1 in 3 segments disappears in spoken language. So I have no solution other than that I would be very, very interested in seeing what is going to happen to these kind of trees if you would have the information, maybe just for, say, modern varieties of spoken spontaneous speech. There are some corpora that are far not enough, but you would take the way that people normally communicate, because you talk about transfer across languages. It's probably happening in that vernacular. If you have contact. So I think that is an area that could be very interesting to explore. But it makes me very afraid to do so because it's so complex.
I mean, in dialectometry, you've been involved in studies like this, so people do this to a certain degree, right? And in principle, what we are doing is just, so we need different statistical models, but the first step of working with the primary data should be the same. So my vision would be that 20 years from now, the primary data we use are really sound recordings from ecologically valid conversations among people, right? And then probably we can't follow the pipeline of the traditional comparative method, but use features which we don't understand, but the machine understands, which are indicative of genetic ancestry of languages, like in phonotactics or in contexts so of word vectors, something like this. So infer informative features from sound recordings and then do phylogenetic inference with those features.
Would be very cool.
Of course, we have I mean, getting data on such a scale, but there's actually a lot of data lying around and waiting to be,
digitized.
standardized and digitized. So probably once everything has been brought into uniform format, we will have quite a lot.
Yeah, but probably also requires a kind of, how do we look at data collection? So here, Roberto and I are working on collecting paradigms from a PAML language. Yeah, and rather than just asking for word list, we now get video recordings of a native speaker reading out these. Now, it's still not spontaneous speech, but at least we have full data. The tone system is by far not clear, as I understand from Heriberto. So we will have real recordings in which we can trace the F0 contours. We can look at how much of the segments are reduced or not. It's still a high level register of producing meta-linguistic data. But if in the field we get the kind of standard that eliciting means recording, and having recording stuff means that you also digitize it and make it available, I think that would be really cool.
Yeah, I fully agree. So working with transcriptions, they have varying qualities. That's the first problem, right? And
people don't agree on them.
There's problems with this, but we have to work with what we have, and we can do a lot with these poor data already.
Oh yes, it's amazing. It's amazing. Okay, those were my questions, Heriberto.
That's great. And I think is on the right track of these questions that are in the chat and myself. Let me just ask, because this is very, very interesting. Just as an anecdote, I mean, but quite relevant, is that when I was at the MPI, one of my tasks was at some point was to infer what was the language of Neanderthal. Talking about Indo-European, reconstruct the thing. And I spent quite a lot of time measuring vocal tracts of whatever Neanderthal was in the world. And I don't know, it's really interesting scientific question. But
I mean, what language they spoke, I don't think there's any way to figure this out, but whether they spoke and what kind of language they had.
Right. I mean, because
this is in principle knowable. Yeah.
You see, and then the actual final answer was at the beginning. I mean, I didn't need to measure all these skulls and traces, X-ray traces. I mean, the vocal tract was able to produce the very same sounds. I mean, we don't have tongues of Neanderthals, and we don't have vocal folds, but just the vocal tract was and good enough to pronounce E, A, U, and everything in between. You see? So, well, anyhow, so that's along the same lines of Indo.
But there's this huge gap. So what I was talking about today was really reconstructing of specific contingent features of languages. And when I started this like 10 years ago, I thought, oh, perhaps I can go a bit deeper than these 6,000 to 8,000 years, but actually I'm not sure anymore that this is possible. And perhaps this is not just a linguistic problem, but also problem with how language families emerged. So many of them emerged with agriculture, and probably, so if we go beyond the last glacial maximum, I mean, there probably there wasn't a lot of diversification going on, which we could track back. So I think Holocene, I think this is all we can do here. But figuring out, there are a lot of interesting studies coming out every year now about how differences, phenotypic difference or the genetic difference might be related, or environment might be related to characteristics of languages. And also Damian was one of the lead authors, I think, of a very exciting paper where actually agriculture was related to the changes in the sound inventory. And language is much less uniform, it seems, than we used to think across humanity.
Yes, absolutely. So let me ask you. So along the same lines of this questions about Harold that Harold posed. So regarding the similarity, the P and I similarity. So the basic assumption here is that the sound is a categorical entity, right? It's a letter, it's a character. Would it be any advantage in adopting a different unit? I mean, still based on a character at a character level, let's say, for instance, as the basis of comparison. So something else that the single letter, I'm thinking of notions or concepts like the demisyllable, where you still have a string, a character, a series of strings, but it's beyond the segment. And I would say that this may be advantageous because that better may better capture the nature of the spoken or oral language, you see, because then you take into account the edges of this character, this unit that the similarity is assuming, you see.
Really understand what you're saying. So the advantage of this approach is that, it's then you can do this dynamic programming, so it's computationally advantageous. So currently I'm experimenting with deep networks, and basically I don't define the features from the outside, but I let the network decide, and then it could come up with actually I hope that it will find something like a phonemic structure within a language and sound correspondences between languages. So this is the direction I'm moving now. So no micromanaging of and feature engineering by hand, but let the algorithm find the features, and then let's check what kind of features it finds.
Right. Yeah. Well, I mean, I'm just thinking.
But something like a syllable or more makes a lot of sense. That this is more informative than individual segments.
Yeah, and also a different but related point is that when you show the dendrogram of similarity, so maybe you have a different one, but this is comparing place of articulation, right? You have labial, you have dental.
Yeah, this is what came out.
Right.
So this is just when I have these similarities here.
Yes.
So red means dissimilar and blue means similar, and it's probably hard to see here, but here you have this blue square. So these are the dentals.
Okay.
Yeah, these are the dentals, and then here we have the labials. So they are mutually fairly similar. And then these are the uvular sounds, and here are the vowels. So they are clearly separated from the consonants. And the ultimate basis of this is then we have a blue color if we often have pairings of these two sounds.
Yeah. So the question for that is that very often sound change has to do more with the acoustic perceptual dimension rather than the articulatory, right? So, for instance, one example that is repeated across languages, and not only in the languages of my expertise, but also in Romance languages, is the change of p, the labial p sound to qua, right? So, and if you see the articulation, it looks so distant, right? Labial to velar, labial velar. So, however, this is a rather common sound change. So that is better understood in terms of acoustics rather than articulation.
So here the P has a lighter spot here connecting to the H, so it's not to the Q or something like this.
Well,
I mean, there are lots of sound changes which do not keep place of articulation constant, but I mean, this method, it's coarse-grained, it picks up the strongest signal, and the strongest signal seems to be, well, we have an F becoming a R, or a P becoming an F, or a D becoming a R. So this is just very frequent, and then a TH sound becoming an F, as it's currently happening in English, I believe. Yeah, this is also happens, but in total less frequent, much less frequently than these, where you just change the mode of articulation.
Well, that's great. So these are my questions. So I just want to congratulate you because this is I like this big picture type of approach. So you are taking the whole world, and this is very exciting. Actually, it's nice. So thank you for that. So let me read some of the questions in the chat. And so, for instance, we have regarding disadvantages. This is at the very beginning of your slides, your presentation. Is how can you include expert knowledge of scholars into a more mathematical computational model? I think this is sensible because some of the harsh criticism of the traditional linguists have been like, you mathematicians are taking our data, our knowledge, and put it into the black box and producing something. So do you think that
this kind of concern, that this was voiced also when Russell Gray and Simon Greenhill and these people started doing this kind of work, but now it actually seemed that a lot of jobs actually were created at this Max Planck Institute in Jena or now in Leipzig, because you need high quality data, and for this you need people with domain knowledge, and you need to evaluate the outcome of your studies, and for this you again need domain knowledge. So I don't think that this will replace linguists, but it supplements it. And also in constructing new algorithms, I just read a very interesting interview in the Frankfurt Allgemeine Zeitung, one of the big German newspapers, between Hans Uschgereit, a computational linguist, and his son Jakob Uschgereit, who is one of the cracks in machine learning. And they said that the information about how language works helped actually the computer scientists to construct these transformers, which are now all the rage in this GPT-3, etc., or ChatGPT. So some broad-scale knowledge about how language works can also go into constructing architectures for machine learning. So, for instance, the idea I just mentioned, that you look at correspondences inside the language, but also at correspondences between cognates. So this is something, as a linguist, I know there must be relevant information, and then I can hardwire this into some neural network and then see what comes out. So I think it's really an iterative process. You need domain knowledge and you need technical expertise to really get the full potential of what's possible these days.
I see. Great. And then we have more questions. Have you explored the correlations between grammatical evolutionary traits and sound-based ones? For instance, final deletion in Latin got rid of case. With a few exceptions, Romance languages did not preserve case. And I think this is sensible, because case in Latin was at the end of the word. And then you have lenition processes that got rid not only of the sound, but the grammar conveyed by this portion of the sound, right? So have you explored these correlations or something along those lines?
Not specifically. There are a lot of people are looking at doing something like this, but using typological features like the World Atlas of Language Structures or GramBank, so kind of Waltz 2.0 has just come out, and compare what kind of phylogenetic trees would we get if we just use grammatical features. The main problem with grammatical features is there are just so few of them. And with words, there are so many of them. Apart from that, so overall, the signals are not totally different, but with characteristic outliers, right? You have the Balkan-Sprachbund, so which gives you a strong, non-tree-like signal, for instance, inside the Indo-European languages. And you get this convergent evolution that East African languages and Southeast Asian languages look kind of similar because they are isolating and have little morphology. So you just have fewer degrees of freedom when you look at syntax or at grammar in general. I mean, the good thing about words is that there are so many of them, so we can do statistics. But you can use words, infer a tree, and then this is basically what I briefly showed you at the end of the talk. And then you can use the tree simply as a statistical model to study the evolution of some grammatical features, like here, case marking systems.
Yeah. I think Fabrizio has a question. Fabrizio?
Yes, thank you. My question is related exactly to this word order thing. I should know this, but I don't. I don't actually remember when. There is this. I'll make it very like. I'll make this.
It's actually not word order, but case marking. I have a similar study about word order, which are both not published. So shame on me. Which you may have seen in one of my internal talks. So
okay.
This is case marking here.
There is this. Well, this is not mathematically proven or with data, but we know that there is SOV languages or VSO languages tend to have more intransitive verbs. There's a lot of studies. John Hawkins in the 80s, 90s, 2000, he showed this, and he even has some explanation for this. And many people see a relationship between this intransitive bias and the rise of ergativity, and then different types of marking. In since SOV and VSO languages have tend to have ergatively case marked transitive subjects, but more zero marked absolutive cases. I was just wondering if in your study if you have something that serves as evidence for this fact that we have intransitive verbs, and then we have then the appearance of ergativity, and then full transitivity.
So I didn't relate this to word order at all. So it's actually an interesting thing to look at. And this Gentile statistical approach used the world tree or something along those lines. Use trees to control for common ancestry, and then look at the diachronic correlations between different typological features. So this is the kind of question which can be tackled with this method. So perhaps we should sit together and
yeah, definitely. This is something I'm interested in. Yeah, great, thanks.
Excellent. This is so great. So I don't think we have questions. Just people congratulating you on the YouTube. Felicidades, muy buena ponencia. Congratulations, very excellent talk. And so on and so forth. So that's great. So let me just comment on just by passing this comment by Harald about the honorifics in Korean. I've been looking recently to remnants of old words, let's put it this way, informally, and parallels or cognates that develop from the same word. So, for instance, just to give you the example of what I'm talking about is in Latin, the group KT, Villar T, like in words like lacteo, docto, are preserved in Romance languages, but in a high level register. You say docto is a very knowledgeable person, or this the adjective, but you have ducho. And ducho is this very same cognate, but this is a more colloquial way of saying you are knowledgeable of something. You don't say I'm doctor in playing guitar, or if I'm ducho in playing guitar, it implies quite different things, you see? And then the point made by Harald is quite relevant, because in the same language, the contemporary language, you have these two registers that can be explained by who was using docto and who was using ducho, the vulgar, the low-level Latin, you see, almost Romance language. So it's quite interesting.
I mean, I could imagine, I'm not a Roman scholar at all, but I could imagine that actually the higher level version, that this was actually borrowed from Latin later, and that the lower level version is actually the genuine cognate.
Yeah.
So somebody pointed out to me that my examples of persona cognate, that these are all borrowings actually, which were vertically borrowed from Latin into, I don't know.
In the 17th century.
Yeah. So
Yeah.
I mean, yeah.
And just to finish, so I've been looking into Yutostecan and Mayan and Otomangan, and Mayan is quite interesting because we have the epigraphy, we have the written form of the classic, and it seems that this is working for that. So it's somehow,
Cool.
yeah, interesting.
And how old is this? So this is 1,000 years or something, or
well, the classic, you can go between 3,000, 4,000.
Oh, so deep. Okay.
Yeah, it's
Thing, huh?
good enough to be a different language. It was Cholan languages, I would say. Anyhow, thank you very much. So
thank you. Thanks for the discussion and the questions and the nice words.
It's great. It's really fantastic and inspiring and great. Thank you. Thank you, Harold.
Well, thank you, Gerhard.
We'll see you next time. So stay tuned.
Okay.
Bye.
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 Okay.
Instituto Nacional de Antropología e Historia.
Secretaría de Cultura.
Gobierno de México.